relate between the output of the system to the input of the system, right? So once we get the model, okay, once we get the transfer function, the ODE model, okay, from the transfer function, we can study the performance of the system. Okay, one of the performance that can be, one of the analysis that can be done on the system is what we call as time response analysis. Okay, so here it defines the time response is a study where we see the output, how the output of the system changes when we apply the input to the system. Okay, so when we say the input to the system, meaning there is a set of common test input that are applied to the system. Okay, so meaning we apply those common test input signals, which are step signal, impulse signal, sinusoidal signal, and ramp signal. Okay, we apply that to the model, to the transfer function. Okay, and then we want to see how the output variable, change in time. Okay, changes in time. Okay, so meaning we apply the input, whether the input is step input. Okay, so we can see here, this is a typical common test input. The first one is very popular, which is what we call as step input. Okay, sometimes you may also see a word like unit step input. Okay. So meaning unit step input here means that we apply 1 unit of input. So the input is 1, okay, and then we apply 1, and then it stays at 1 all the time. Okay, so here is the time. Okay, x axis is time, represent the time, and then this is for the input, we normally call it u. Okay, so if you see the type of input is like this, so we call this as a step input signal. Okay, if the unit is 1, we call it a unit step input. Okay, sometimes it does not show you the value, but it just mention unit step input. Okay, so you should understand unit step input meaning the input value is 1. Right, and the second one is impulse signal. Okay, impulse signal. So impulse signal is when the input is applied and then straight away goes back to 0. Okay, only one time. Okay, so only apply one time, and then straight goes to 0. Like just you macam ketuk sekejap lah, sekali je. Okay, ketuk dan lepas. So that is example of impulse signal. Okay, other than that, common step input signal is sinusoidal signal. Okay, sinusoidal signal. We have A here, the amplitude, and then also we can determine the frequency there. Okay, and then the last one is ramp signal. Okay, ramp signal is when you apply the input is increasing with time. As the time increase, the signal also increase. So this is what we call as ramp signal. Okay, so we apply this one of this signal to our system, to the transfer function, to the model, and then we also want to see how the output will also change with time. Okay, so y is normally the output. Okay, so we're going to see how the output change with time. Okay, either it's changing like this. Okay, it will depend on the type of input actually. Okay, or something like this. Okay, or something like this. Okay. So you can see the output variables will change with time when we apply the input. So this is what we call as time response analysis, or short name time response lah. Okay. All right. So in time response, okay, there are two parts. Okay. The first one is what we call as transient state response. Okay, and the second one is steady state response. Okay, so transient state represent a region when we apply this input signal. Okay, when we apply the input signal, so the output signal will also change, but it will take some time before it reach steady state. Okay, so here is when it reaching the steady state. Okay, so before that you can see that the response is dynamic. Okay, the response is keep changing. Okay, but after some time it will reach at one stable value. Okay, meaning there is no more changes in the output there. So when it reaches that state, we call it is reaching steady state response. Okay, so before that we have a transient state, and after it reaching steady state, we call that as a steady state response. Okay, so transient is starting from initial to the final state, which is to the one stable value. Okay, but once it reaches stable value, the value will not have very much changes in there. So maybe in plus minus 1% or so. So when reaching that condition, we call it as a steady state. Okay, so the steady state is a system output behave as the time approach infinity, meaning even though you increase the time, you let the system run along the time, but it will not change very much. It will stable at one value there. Okay, so for transient state, normally we have a dynamic transfer function. Later in the transfer function, you also can see there is two type of transfer function. The first one is dynamic transfer function. Okay, so dynamic transfer function is used to represent the behavior in the transient state. Okay, and then for the steady state region, we have apa nama dia? Okay, it is, the name is what we call as static transfer function. Okay, so two type of transfer function, dynamic transfer function. Okay, meaning we can see the transfer function will explain the behavior in transient state. Okay, but after it reaching steady state, there is another transfer function that will explain the behavior at the steady state. This is what we call as static transfer function. Right. So what we're going to do in this chapter is from a model, from a transfer function that we derived in the first chapter. Okay, we want to get the time response equation. Okay, or time response transfer function, which is actually comprised of dynamic transfer function and static transfer function. Okay. So in order to do that, okay, in order to do that, we're going to do a few steps. Okay. Okay, which the step mana step dia? Okay, saya just mention je lah dulu kat sini. Okay, the step is first you need to have your ODE model. Okay, because we know that the transfer function is in ODE model. Okay, and then we're going to transform it into Laplace form. Okay, after it's all in Laplace form, we're going to apply the input. Okay, so step input we have we'll have the representation in Laplace. Okay, impulse input, sinusoidal signal and ramp signal also have their own representation in Laplace. Okay, so we're going to apply the input. After we apply the input, we're going to apply the initial condition. Okay, maybe it have a zero initial condition, meaning at initial all the value is zero. Okay, or maybe it's already have some value there. Okay, so we're going to apply the initial condition. Once we apply the initial condition, we will solve for the parameters in the Laplace form there. Okay, so you're going to use a partial fraction method in order to solve the equation. Okay, once we solve the parameter, we get the value for A, B, and C in there. Okay, so after we solve for that, we're going to inverse back into the ODE. Okay, so lastly, we will get something from a ODE model. We get yt is equal to, let's say, this 1 minus exponent negative t. Okay, so this is an example of the output after we inverse from Laplace. Okay, but before we go to the step, let's start with the ODE. Okay, so I already explained that the transfer function of the system or the model of the system normally represented in the ODE type model, ODE, ordinary differential equation model. Okay, so when it is related to ODE, we're going to use a Laplace form in order to solve the differential equation. Okay, I believe you already know this equation. Okay, this is the general ordinary differential equation. Okay, so we can see that dyn y per dt, y is the output, y is the output. Okay, u here is the input. Okay, n is the order. Okay, order for the output. And then m is the order for the differential equation for the input part. What else? Of course, we have d per dt there. D per dt, differential, because this is differential equation. Right, that's it. Okay, this is the ODE. Okay, so you can see in ODE normally one side we have output, and this side here we have input. Okay, so you can see all the term that contain y, the output will be at one side. Okay, and at the other side is all the term, all the part that contain the term for the input, which is u. Okay, and then of course when we talk about ODE, we have initial condition. Okay, so we have y0 equal to 0. Okay, meaning y at time 0. Okay, dy0 per dt. Okay, dy0 at initial condition, time 0, dy0. Okay, dy per dt, d square y per dt square. Okay, d cube y over dt cube. Okay, and normally n is always bigger than m. Okay, the order for the output will always bigger than for the input. Okay, because n will become the denominator, m will become the numerator. So the order of denominator will always bigger than numerator. All right. Right, so let's see one example here. Okay. So in this example, okay, we're going to derive the differential equation for the transitional system in this system. Okay, so basically we just repeat what we have done in chapter 1, but instead of drawing a block diagram, we're going to put the equation in terms of ODE. Okay, so the step is still the same. We're going to do the free body diagram. Okay, we have M, then we have force, we have damper. Okay, consider I bigger than 0, so the spring is in compression. Okay, so the reaction will be force M to that. All right, so therefore we will have F spring plus F damper equal to md square x naught. Okay, so F spring is k xi minus x naught plus cd xi minus x naught. We directly replace Fs equal to ksi into minus x naught into this equation, into the mass equation. So this will be equal to md square x naught. Okay, so in order to have an ODE equation, we need to separate from the input and output. Okay. 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 So let's say we have here kxi minus kx naught plus cdxi minus cdx naught equal to md square x naught. Okay. So we're going to put the output on the left side and the input on the right side. Okay. So therefore you're going to have md square x naught, okay, md square x naught, okay, plus cdx naught plus kx naught, which is all the term that contain the output. The output is x naught, equal to the input side. Okay, so the input side is cdxi plus kxi. Okay, so we can see here md square. Okay, d square here is represent d square t over d square x over dt square. Okay, so it's already in the ODE because d is d operational. Okay, so here is our ODE. Okay, so in order to solve for the ODE equation, okay, we have a few steps there. Okay, the first one is, in our example here, we produce the ODE. Okay, the example one show that how to produce the ODE model. Okay, and the second one, we need to transform ODE to Laplace. Right, once we have the ODE here, we already have the ODE here, md square x naught plus cdx naught plus kx naught equal to cdxi plus kxi. The next step is to convert this ODE into Laplace form. Okay. All right, the third step will be apply the initial condition. Okay, once we convert into the ODE, the Laplace form, we apply initial condition to that. Okay, after we apply the initial condition, then we apply the input. Okay, so U is the input, so it depends on the type of input. If it is a step input, then you're going to apply step input in the Laplace form. Okay, step input in Laplace form is 1 over S. Okay, if it impulse input is 1, sinusoidal input, there will be the form for that. Okay, so we apply the input in Laplace form. Okay, after we apply the input, okay, we will do the step for the partial fraction decomposition. Okay, you're going to separate into partial fraction. The objective is eventually to determine the parameters for the Laplace form there. Okay, so using partial fraction, we decompose the ODE into several parts, and then we solve for the parameters. Okay, once we already solved for the parameter, then only we're going to inverse Laplace. Okay. Okay. We're going to inverse the Laplace equation. So lastly, what we get here is we get YT, which is what we call as the solution for the ODE. Okay. So YT here we represent the behavior of the system. Okay. So if we plot YT, you should be able to get some response. Okay. For example. Okay. So the equation of YT will allow you to plot this kind of graph. Okay. Any questions so far? Any question? Okay, let me summarize again. All right. So the objective is to get YT. Okay, to get YT, meaning we want to know how the output behave when we apply the input. Okay, so in this case, we want to know how the output behave in time. Okay, when the time changes, how the output change in time. All right. So in order to get that, okay, we need to have the ODE of the system. Okay, the ODE here is also known as the model of the system that relates between the output to the input of the system. Okay, so we can get the ODE from the system itself. Okay, this is shown in example 1. Okay, so we produce the ODE model from the system. Okay, we do the free body diagram and then we get the ODE. Okay, so once we get the ODE, there will come step number 2, which will need to transform the ODE into Laplace form. Okay, this is the step number 2 that we're going to learn after this. Okay, you already learned about Laplace form in calculus, in ODE, in mathematics berapa ODE lah, the course is ODE, right? Okay, so you already learned how to convert from ODE into Laplace form. Okay, so I'm not going to repeat in detail. I just want to show in how to use the Laplace form for the control application. Okay, so we're not going to do all the inverse, exponent, negative t, adalah dia punya form tu kan, integration of 0 infinity multiply with function multiply with exponent negative t tu. Okay, we're not going to do that. Instead, we're just going to use a table. There's already a table for that. For that, we're just going to use that for the purpose of control application. Okay. Alright, so after you transform into Laplace form, then we're going to apply initial condition. If there is any initial condition, we're going to apply that. Okay, then we're going to apply the input. Okay, it will depend on the type of input, whether the input is step input, ramp input, sinusoidal input, impulse input. So we're going to apply that. Okay, and then we're going to solve, we're going to use partial fraction decomposition method in order to solve for the Laplace parameter there. There is some parameter that we need to determine in Laplace. And then once we get that, then only we can inverse the Laplace equation, the Laplace form, into the time response equation, which is yt equal to something. All right. Okay, this is the second step, which is Laplace transform. Okay, this is the general definition for Laplace form. In order to get a Laplace transform, you need to multiply a function in time, the ODE in time, multiply with the exponent negative st, and then integrate 0 to infinity dt. All right. I'm not going to touch this. Instead, we're just going to use this table. Okay, because it is always not necessary to derive the Laplace form each time. Okay, there is already Laplace table that can be used conveniently to find the transform of given function. All right, so we're just going to use this table. Okay, because the function is standard. It's a standard function, so therefore we can just use the table, the transform table here. All right, so let's understand this table on how to use this table. All right, on this side here, okay, it is in terms of time. Okay, the equation is in time. Okay, so you can see the first one is impulse input, step input, ramp input, and polynomial input. Okay, unit input, unit step input, unit ramp input, and unit impulse input. Okay, so you can see if your input is units impulse input at t equal to 0, okay, meaning at t equal to 0 there will be impulse equal to 1 because it is unit impulse, so the value is 1. But if it is not unit, maybe 2, so this one here will become 2. Okay, so it depends. In this table, it shows just for the unit impulse. Okay, same goes to the step input. Okay, because it is unit step input, in Laplace, the function will become 1 over s. Okay, but if the unit is equal to 2, okay, for example, if the unit is 2, okay, so in Laplace, it will become 2 over s. Okay, 1 over s when the unit is 1. Okay, the step is 1, right? So it 1 over s. If the step input is 2, then the Laplace form will become 2 over s. The same goes to the unit ramp. Okay, if it is unit ramp, 1 over s square. If not unit, if it's there is some value, then you can have 2 over s square. Okay, and then you also have polynomial. Okay, right, this is polynomial form. Then this is the Laplace for the polynomial form. Okay, that is something not very common. Okay, this part is a very common part that we're going to use. Sampai sini lah, sampai sini. Sebenarnya basically all this table is a common part, common function that that always in the control application. Okay, so you will have exponent negative alpha t. Okay, in Laplace it will become 1 over s plus alpha. Okay, sine wave alpha over s square plus alpha square, cosine wave, then sine wave, and then cosine wave, right? So this side is for the time, and this side here is for Laplace. Okay, we are also going to use this table when we're going to inverse from Laplace into time. Okay, so again, we're going to refer the same paper. All right, the most importantly is this part here. Okay, because we're going to transform ODE into Laplace. So basically, for example, in the equation just now, we have md square x naught plus cd x naught plus k x naught. Okay, I just take one side of that. Okay, so you can see there is first differentiation. Okay, here this is first differentiation because d here is d over dt. Okay, and d square here is the second differentiation. This is d square over dt square, second differentiation. Okay, and then this is just a constant. Okay, so this is not. Okay, so when there is a first differentiation, like CD here, first differentiation. Okay, so in Laplace, you're going to transform that to become SYS minus Y0. Okay, so here you're going to have, for example, first differentiation, we have CDX naught, CDX naught. Okay, that is the first differentiation. So when we transform into Laplace, so it become C S X naught S plus X naught 0. Okay, so that's how we transform from ODE. The ODE, the term is CDX naught. Okay, so in Laplace, so it becomes C multiplied with SS naught, SS naught S plus X naught 0. Okay, which is based on the term here. All right, and then we have our second differentiation. Okay, for example, we have MD square X naught. Okay, right here, MD square X naught. That is in form of second differentiation. So when we convert, it will become M multiplied with S square X naught S minus S X naught 0 minus X naught prime 0. Okay, so that is for second differentiation. Okay, normally for your control cost, it will be up to maximum second differentiation. Okay, but if you're going to use it in real application, later on you do PSM or you do PhD or you do master, and your system is higher order, higher than 2, so you can use this general ODE differentiation to the Laplace form. Okay, so if you have y, if you have y3t, okay, meaning the order is 3, so you're going to follow this. Okay, so it becomes S3 ys plus S2 y0 minus S y prime 0. Okay, itu je lah kot. Minus n plus 1 n plus 2 tak adalah. Okay, right, so you will have ni dah satu kot ni. N minus 2 dah 0. Ada satu term 3, 2, 1, 0. Ni. Akan ada last term ni. Last term mana ni? Felix nampak. Okay, last term dia adalah Y. Y0, SY prime 0, then akan ada minus S2 N tolak 1, 3, 2, S1, S1 lepas 1 Y prime, SY prime minus 0. Ada 1. Macam tak ada dah. Okay. Tak ada. Okay. Just left with S3 YS minus S2 Y0 minus S1 Y prime 0. Okay. Right. So that is if your order of the system is higher than 2. Okay, you can use the general equation here. All right. Any question on this table? Okay.
Kalau exam ataupun test, nanti table ni bagi ke?
Biasanya bagi. Biasanya table ni bagi untuk exam. Biasanya bagi. Biasanya bagi. Okay, tapi mungkin tak full macam ni lah. Mungkin some of the part. Okay, tapi basically dia bagilah. Okay. Alright. Alright. So let's see how we can use let's see how to use the step just now. Okay, I showed you 7 steps just now, and we're going to apply onto this example 5. All right, so here we have a spring damper system. Okay, spring damper system. Okay, the question is to find the time response x naught t. Okay, for a unit step input. Okay, it's mentioned here. It is unit step input. Okay, and then the initial state is given. X naught 0 is equal to 0. Right, so that will be step number 3 and 4 then. Okay, so first, of course, we're going to find the equation, right? So we know F spring minus S damper equal to 0. Okay, so we do know that for the F spring, K xi minus x naught, and then for the F damper, it is CD x naught. Okay, because the damper is only relate to x naught. Okay, the other side of damper is a water. Right, so we're going to put into this equation here. So we have K xi minus x naught. This is the first step in order to get the ODE equation. Right, so once we get this equation, we're going to separate between the input and output. Okay, so we're going to put the output at one side and the input at one side. So we're going to have CD x naught plus KX naught is equal to KXI. Okay, so this is the ODE form. Okay, the ODE for this system. Right, so now we're going to do the second step. Okay, the second step is to do the Laplace transform. Okay, this is the first step, ODE. The second step is Laplace. Okay, So we're going to convert the differential term into Laplace. Okay, so you can refer to the table just now. Okay, so here we can see it contains first differentiation. Okay, because the highest term is only D, so it's only contain first differentiation. Okay, right. So for the Laplace form, okay, so we're going to have C SYS minus SYS minus Y0 plus K X naught S, okay, will equal to K XIS. Okay, so that is in Laplace. Okay, then we can apply the initial condition. Okay, apply the initial condition. And also we're going to apply all the values given there. Okay, so it's also given C is 1. Okay, K is also 1. And then the initial condition is X naught 0 is 0. X naught 0, X naught. Oh, dia pakai X naught. Okay, so second kita kena ubah ni lah. Ni jadi X naught lah. X naught, this is X naught. This is X naught. Okay, this is Xi. Right. So X naught 0 is 0, this one. So this one is 0. Okay, so we apply the initial condition. So it become, the equation become S X naught S, okay, multiply with 1. Okay, then this one it becomes 0. Then plus X naught S equal to XIS. Okay, right. So now before we can apply the step input, we have to write in terms of transfer function. Okay, so it will become X naught S is equal to multiplying S plus 1 equal to XIS. Okay, remember Xi is the input, okay, S naught is the output. Okay, so we have X naught S, which is the output, is equal to the transfer function 1 over S plus 1, the transfer function, multiply with the input, which is XIS. Okay, so now we're going to apply the input. Oh, sorry. Okay, bagus. Okay, so number 4, apply the input. Okay, so the input is step input, unit step input. Meaning XIS is equal to 1 over S. Okay, so therefore here you're going to have X naught S is equal to 1 over S plus 1 multiply with 1 over S. Okay. Okay, so far now it come partial fraction decomposition. Okay, now partial fraction decomposition meaning we have 1 over s plus 1. We have 1 over s plus 1 multiply with 1 over s. In the partial fraction, we equal to a over s plus 1 plus b over s. Okay. Okay, so we need to solve for a and b. Okay, we need to solve for a and b. Okay, so here apa method dia nama? Method dia. Reminder theorem. Okay, tak apa, reminder theorem tu nanti. So basically you will solve for a and b. So for this example, I'm just going to show you. You're going to have x naught s is equal to 1 over s plus 1, and then dia ke 1. Buat partial fraction je. So if we're using partial fraction, reminder theorem, so you're going to have a over s plus 1 equal to 1 over s plus 1 multiply 1 over s with s equal to minus 1. So we can cancel this. So a is equal to 1 over 1. So it is 1. Okay. As for b sama juga b over s equal to 0. Okay, 1 juga. So b sama dengan 1 juga. Later saya akan tunjuklah partial fraction tu, tapi basically for this one saya buat mark ke atas. So you're going to have x naught s is equal to 1 over s plus 1 plus 1 over s. Okay, that is after you have solved for a and b using reminder theorem. Okay, for today we're not going to discuss on reminder theorem yet. Okay, so then there is step number 5, and then step number 6 is inverse. Okay, so you're going to inverse x naught s equal to 1 over s plus 1 over s plus 1 plus 1 over s. So if you inverse that, okay, so x naught s will become x naught t. Okay, 1 over s plus 1, we're going to refer to the table here. Okay, so this is the form 1 over s plus 1. That one. So we inverse here, it will become, so here alpha is equal to 1. If we compare 1 over s plus alpha with 1 over s plus 1, so we can see alpha is 1. So therefore, in the time form, it become exponent negative t. Okay. And the other one is 1 over s here. Okay. So if you if you inverse, it will become 1. Okay. So writing here, it will become 1 over s is 1 plus exponent negative t. Okay, so that is the time response equation for the system. Okay, for the spring damper system, you do all the steps. Step number 1, produce the ODE. Step number 2, transform into Laplace. Step number 3, apply the initial condition. Step number 4, apply the input. Okay, and then step number 5, we do the partial fraction decomposition. Okay, we solve for A and B using reminder theorem. Okay, and then step 6 will be inverse Laplace, where finally we get the solution of the ODE, which is the time response of the system, which is 1 plus exponent negative t. Okay, so that's what we're going to do in time response analysis. Okay, any questions so far? Okay, for the next week, we're going to try example 1, okay, reminder theorem, how to use reminder theorem. And then we're going to do a few examples to make sure you're familiar with some of the function in Laplace and etc. Okay. Then that is for part 1 for chapter 3, which is time response ni lah. Okay.
Doktor?
Yes.
Yang tadi kita dapat tu x naught t 1 plus e negative t tu yt lah tu kan?
Yes, yt lah tu. Tapi sebab dalam kita punya sistem, the output is s naught t, so saya tulis s naught t lah.
So
Tapi
kalau kita plot tu dapat lah graph tu lah?
Yes.
Okay.
Okay. And this equation is specific for unit step input because we already apply a unit step input. Okay. So if your system require different input, so you need to redo from step number 4 here. Okay. So when you apply the input, you need to apply your type of input. Maybe you want to apply meaning the unit is 2 or unit is 3, okay, or impulse input. Okay, so you need to change at step number 4. Okay, the rest is the same. All right, so we're going to stop here. Okay, we're going to continue with next week in few more examples in order to make sure you're familiar with all the steps and also with different function that you can find in Laplace. Because ODE and Laplace, there are many function, dam, undam, banyak function lah, banyak jenis, kuasa 2, kuasa 3, semua-semua tu. So ada beberapa step yang basically in mathematics you need to familiar in that, so that you'll be able to solve for the function. Basically that is pure mathematics. It's not related to control, but in order to solve a control application, we need to have that skill. Okay. All right. Thank you. Assalamualaikum warahmatullahi taala wabarakatuh.
Thank you, Ada.
Thank you, Doktor.
Thank you, Doktor.
Thank you, Doktor.